Okay, that's something where you've seen a couple times already how it's actually done. But nevertheless, there's a little bit of background that you need to know. It's about calculating scales. So we're here. All the stuff covered up to there, all the regression all done. We now continue with the scales part. That is, in fact, only one command. That's called alpha. You've seen before already. And parts of that are in chapter 12, and there is a reading guide online that will help you find these parts in the chapter itself. Okay, so let's see where this is in your standard run of doing something with data. We start from, okay, I get my data in, I check my data, I think about what it is that I want to do here, the t-test, the chi-square test, or who knows what kind of test, and there is stuff there where I want to somehow deal with my data so that I get better measurements than the ones that I have. And all the stuff that I'm about to tell is typically what you do before you run your actual analysis. So before you run a multiple regression, you would try to calculate a Cronberg's alpha. And in fact, when we did it before, we've seen that alpha command before, that this was also typically before we actually ran a t-test or a regression analysis. So it's somewhere over there, more measurement actually than it is true analysis. Okay, when do you do this? There is a clear reason for this. Whenever in a survey or in an experiment, there are things that you want to measure that are not easily measured by just asking a single question. I want to know how old you are, and I ask you, okay, how old are you? You give me a number, and that's exactly the number that I need. And you know, all kinds of measurement errors might still happen, but at least I know that, you know, that's the thing I want to know, and a single question is good enough. And for several of these, that doesn't work so well. One of them was happiness. We've calculated this, I think, in one of the first lectures. It was also in our own survey. And you try to ask this in a straight way with just one question. For instance, like this, okay, how heavy are you on average? And give me a number, to be -5 or +5, or you know, anywhere from 0 to 5, or whatever scale you want to use. What you can argue against this is, well, -5 to +5. Yeah, this is only one question, so the best that I can get here, and usually the end point is typically not used by people, so this will give me in the end a scale from, let's say, -4 to +4. And that is the only amount of resolution that I can get, because I do not allow a -3.5 here. So that's the only thing that I get. The other thing is, guys, it's not so easy here. We're asking now our respondents to themselves average out across, let's say, a year or so. This is also not very nice, because not everybody does the same thing. If you are in a bad week, perhaps you give a lower number here. And there are, that's the other thing here, typically for happiness, different kinds of happiness are usually measured. One would be, let's say, your general lifeline. How do you feel in general? Not the kind of ecstatic yes experience that you might have. So that's also something else that you could ask here. And then here, yeah, what do you want to know? How often in a year did you have that in the last week? Not so obvious. So one thing to do would be, okay, we measure happiness in lots and lots of different ways. For each of these separate ways that we feel that, well, it is something that is related to your general happiness, we hope. It might, to some extent, also be a little bit of noise, but if we have questions enough, then the noise will average out, and at least what we will get is a measurement that is more detailed and better than the one that we have. So these are the things that we can say a couple more. We did ask, for instance, I find coping with life a real struggle. You know, typically something where if you score high there, not a good sign for your happiness. So for each and every one that we have here, we want something that is saying something about happiness, but not completely. And adding up all the bits, that'll work. Okay, so let's, oh, where's that? Yeah, I had this. Yeah, we call these separate questions. If they are in a matrix question, you typically call them items. That's just a bit of jargon. What you typically want in there is that you have positive and negatively framed items. If for no other reason than just to double check if somebody is just giving the same answer all the time, then also the negative ones will get a positive number, so that will also give you an idea as to whether there are people messing up your data. Let's see. No, nothing else that I want to add to this. And this is the idea. We have, let's say, the true happiness value, whatever that may be. That is, let's say, what is underlying all these items. That's the thing that you want to capture in the survey. There is a little bit of separate item value. So if I ask you, I generally rise happy in the morning, then to some extent this has to do with that, your general feeling. To some extent this has to do with the extent to which you are a morning person in general, perhaps. And there might be some noise in there. If this was a bad week where you didn't rise so well, then perhaps you are more probable to say a relatively low number there. So the idea is, if we have more of these, then this part, if we average out, is the only part that will remain. That's the theory, at least. Okay, one thing we're not looking at here is that, well, you could think, if all these questions are about, as in our example, happiness, it could very well be that if there are 2 kinds, or 4 kinds, or 10 kinds of different sorts of happiness, then it might be a good idea to have, let's say, 20 items and then divide them in, okay, this is one kind of happiness, set that aside, and this is another kind of happiness. And in fact, for that you need to do an analysis that is slightly more complicated. It's called factor analysis, and we'll get into that later. But for now, we will assume that with all the item batteries that we have, that what we try to do is measure one underlying concept, and we want to figure out if it's working, yes or no. Okay, so this is the one of the earlier applications of this idea, and relatively recent. It was, let's say, resurrected by this book by a guy called Surovicki, The Wisdom of Crowds, where the story that goes behind it is, well, there was a fair, braderie, zou je hier zeggen, where the idea was you have to predict the weight of an ox. And I don't know, there must have been a prize connected to that, and if you have it right or are closest, then you get the ox or something. And the idea was there, or the surprising finding was actually that if you look at all these separate estimates, then all these estimates need not be that great, but the average of all these estimates, that's typically a very good estimate of the true weight of the ox. That was in 1905, Galton, who noted this and came up with that idea. And then Surovicki came up with a similar idea in different kinds of contexts. If we just average out, let's say, data from not necessarily even experts, then even that will be good enough. And that hypothesis, well, that will work when, if you have a couple of things, you have diversity of opinion. So it shouldn't be that we all huddle up and try to come up with a weight for the ox. We each think about these kind of things independently and each give a number. That's what we need. If you don't have that, then it's not likely to work. Independent thought, the whole idea is that each and every one of you has, let's say, a piece of the puzzle. For instance, you look at the ox and you think you know nothing about cattle, but you know something about, let's say, cars. And you tend to think, well, that ox is about the size of a Mini Cooper. And I know that a Mini Cooper weighs, I don't know, 700 kilos, or who knows how many, so I'm going to use my estimate to stay in that neighborhood. Might be sort of correct. Somebody else doesn't know that, but knows something else, and comes up with another estimate, and in the end, if you average out enough people, you come up with this independent idea of this, and for that you need also that there is at least a little bit of truth in it. Then you need a good estimate. And you need the local knowledge, so it shouldn't be that you have, let's say, 1,000 estimates, all of individuals with the same kind of knowledge. It helps if you have really diversity of opinion here. That'll work. Also, by the way, the quiz first. As you saw, if you would take all the answers that were chosen the most, then for 2 or 3 questions you would have missed, and the other ones you would have had correct. So in that sense, you would have scored 34 or so out of 37, so quite good. Okay, exactly when it works is still not completely clear. In this book, you see a couple of, let's say, very convincing examples, and I'm quite sure that there must be examples that are far less convincing, but they don't make it to the book. So when and how to use this is really not exactly clear. People have tested the same idea here. In fact, here you have, Who Wants to Be a Millionaire? Is that called, may even be called exactly the same thing on Dutch television. I'm not sure if it's still on now, but it was for quite a few years, and there you have one way out if you do not know the answer, and that is ask the public, where the public is only the public in the studio there. And people have actually tested whether or not this is working, and a good rule, this was done not on the Dutch version, on the English version, I think, is, well, if the top answer that the audience chooses has more than 50% of the votes, then just go for it. That will be correct in 93% of the time. Quite good. If there is a 20% difference between the first and the second answer, if the top answer itself is not more than 50%, then still take 92% chance that you'll have it correct. If none of these holds, okay, then you're on your own. It's not obvious what to do anymore. But still, in quite a few of these cases, this will actually work. Asking the public. And a bit of background on why that might be. Well, let's say that the true answer is B from a multiple choice question. And then we have 4 groups in the audience. There's only 20% who actually knows the right answer B for sure. So that's still not very, very good in terms of how knowledgeable the audience is. 10% knows that it's certainly not C and also not D, but nothing else. 30% knows that it's not D, and 40% is just guessing. So if you don't look at this further, then you would argue here, well, the audience basically doesn't know what the answer is, or not very well at least. What you will get is, well, these will choose B. These will randomize between C and D, between A and B. So let's say 5 on A and 5 on B. This one, this group will exclude B and randomize between the other 3, and the other 40% will just randomize altogether. If you add all these numbers up, you get 45 over there, B being the correct answer. So even in an audience that is not very knowledgeable, as you see in this example, this will actually work. You do not need a lot of smart people in there. And of course, something else that I emphasized before, typically what we go for in many sports, for instance, is that you want to be able to be good on average in the long run. Right? We do not decide a darts match by throwing a single dart. Would also be much less of a TV sport then, of course. But it's also more honest. If I'm better than you, then if I have long enough time to show you, then it's more natural that I would win in the end. So here you see this happening as well. Okay, so let's see. Back to the methods part. We have for these items 2 kinds of things that we would like to know: reliability and validity. These are not the same, and this might be a graphic that you've seen before in that respect. So in the first method scores, it must have been about this as well. This would be reliable, but it's not valid. So same score more or less all the time, but off. So that's like standing on a scale, and it says 126 all the time. And even though you know that you weigh 80, it's reliable in the sense that you get more or less the same number every time, but it's not valid because it's not weighing what it's supposed to weigh. This is not very reliable and not very valid, sort of random noise. This is, low, I should say. Yeah, depends a little bit on what you call low and what you call not. This is totally off, for sure of that. And there is variation in measurements. So this is like a scale. I'm going to stand on the scale, and it is way off and different numbers off all the time. And obviously what you do want is something like that. Now what we will look at, the only thing actually that we can look at with Stata is not so much at the validity, but at the reliability. So all that validity stuff that you may have seen before, this is part of the first method scores. All the validity stuff is about, is this thing really measuring what it is supposed to measure? There is no way how you can do that with the data set itself. You might want to measure something on the outside that should correlate with it. That could be within itself. With just the item battery, there is no way to do it. And the only thing that we'll do is look at the reliability. From these, you've seen 4 as well. And I have put the slides from the method scores online, exactly from the part where I think Gerard Rooks or Peter Ruiter has discussed this part. And from the reliability, we only do this part, what's called internal consistency or inter-item reliability. There are other forms, but all these we won't be able to do. And it's easy to see why that is. First, test, retest reliability. In principle, we could do that. That is, we measure it once, and then we measure it again, let's say 2 months later. And now we check if the values that we get are consistent. And okay, we didn't measure twice, so there's no way to do it. Alternate forms reliability, well, that is typically when you have, let's say, 5-point items, and what you do is you change nothing in terms of the wording, and the only thing that you change is now you change to 7-point items. You do the whole calculation stuff again, and now you compare whether or not the results that you get are consistent. Again, for that we need a second measurement. We'll do this again. That in principle we could have done in a single survey, you know, one matrix question and then the same one afterwards, but now with different item categories, but I didn't. So it's also not what we can do here. Then independent raters evaluate something. Okay, this is in this case not appropriate at all. You know, you are the only one rating yourself. And in principle, again, we could have done it differently. So we ask you to rate her on a bunch of items, and then we ask you as well to rate her as well, and then we see if it makes any sense. But you know, for these kind of things, we typically do not have it, which leaves only one thing to do: the inter-item reliability. Okay, how does that go? Easy. First thing to do is, and typically something that people tend to forget, read the actual items in the data set that you get. Don't just look at the alpha command and then go by the statistics. Look at what's being asked here. And one thing you see is that the ones in red over here are all phrased negatively. The other ones are phrased positively, and the red ones are phrased the other way around. So that's the first thing to note. Which of these are or should be the other way around? In this case, we had strongly disagree as number 1 through strongly agree, that is 6. And in the example that I show in a minute, that's data from 2 years ago. So we have these same questions in the data right now. We can do this as well. And in all likelihood, what you will find for us is slightly different from what you will see over here. So this is first if I show what I've done before. I run that alpha command. That star is saying, okay, look here at all the variables that start with the word feeling and then something behind it. Generate a new variable that's called happy, and I ask item, and that item that will give me this table. If I don't ask for that item part there, I only get the last line. And that will in the end give me a number, and let's say the main number that we should have a look at is this one. This is the scale score, and this value we want to be relatively high. How high, I'll look at that in a minute. What you see here as well is that this is one of the few commands actually in, well, at least that we are going to cover, where having missings nevertheless causes that all cases are included. So if you would run a multiple regression, let's say with these variables in here, and you see here that the number of observations, okay, let's see, here is 101, so there must be one person who has no score on feeling 7, same here for feeling 12. If you run a multiple regression, these cases will simply be thrown out. They are not being used. That's not what is happening here. What that alpha command does, in principle, I'll talk about this more in detail, but it averages out the item scores after first mirroring the ones who are scored negative, and then it averages out over the cases that it has. So if there is somebody in there who has feeling 1 through 6 and has missings on 7 through 17, nevertheless, this person will get a scale score. The scale score will then only be based on the first 6 and not on the other ones. And in a way, the most consistent would have been if that person would have gotten a missing value, because that's the normal thing to do. For most other commands that here, you don't have that. So all the cases will be included here, even the ones who do not have a complete set. Okay, so that's one thing to realize. I'll go into details about what all these numbers mean in a minute, but first let's focus just on that number, that 0.82 that we get over there, and let's look at what it means. There are 2 ways to look at it. One is, well, if these 17 items really are measuring the same thing, then if I would calculate a scale score on the first half and not on the second, and then I calculate again the scale score but on the second half, if they really are measuring the same thing, then these 2 things should correlate quite a bit. Otherwise, they are not measuring the same thing. could do is, well, if I have 17, I split them in a group of 9 and a group of 8. I do that in all possible ways possible, and I calculate the correlation between the two groups for all the two groups that I can create. And that number I average out. And that is the, well, not possible to see anymore, but the 0.82 that you see over there. What you want is that this number is high. If it would be 1, that would be really, really high. That would suggest, okay, if you split the set of items in two groups, and you calculate the scale score here and there, and then you look at the correlation, and the correlation is basically 1. So what you get twice is simply identical. So what we want here is, well, okay, 0.5 to 0.6, that's really not what you would like to have, and it would really be considered poor. And even below 0.5, then so bad that you do not even want to create a scale score. And I would even say that anything below 0.6 is not good enough. Acceptable starts from 0.60. Good starts from 0.70 to 0.90. And over 0.90 you could argue, well, this is of course excellent, but perhaps you could have done just as well with a couple of items less. Because if they are so high, then instead of the 17 that you have used, perhaps using 10 instead would have been enough. There's a trade-off between being able to have a decent scale score and some efficiency, of course. Okay, this is called alpha, and in case you wondered, this has absolutely nothing to do with the 5% alpha that we have seen thus far. So it's easy to mess it up, same word, but it is something different. This is Grondach's alpha, and the other alpha of 5% has nothing to do with Grondach whatsoever. Okay, so let's see what we have. Oh, I forgot one, by the way. Yeah, the other one is a really sort of a mystical way to define what that alpha really is. You can see this set of 17 items as, well, this is sort of a random choice out of the total set of items that could have been thought of. Okay, so we're measuring stuff here that's related to happiness. You know, if I put my feet on the table and I think for an hour, then I come up with 250 of these different items that are all related to happiness somehow. So if you see this as a random sample out of the whole population of items that I could have chosen, then that number over here, that point, was it again, 82, that is what represents the true variance in there. So what I said in the beginning was, okay, if I measure something, we have, let's say, the true underlying thing, something that is particular to the actual item, and some noise. Okay, that true underlying thing, that 0.82, that is an estimate of how much of the variance in there is actually the true variance that you're looking for. Now, there is a little bit of hand waving involved there, because, you know, a random sample from the potential set of all items, not really clear exactly what that means. But there's another way that you very often see how this is typically defined. Okay, one thing before the break. This is what that table looks like. Let's go through what we see here, one by one. First, what's called item test correlation, in that column right after the signs. Oh, and before I forget, the first thing to do here, before looking at all these numbers, is looking at these signs. What Stata does is try to figure out which signs here would cause the highest alpha value over there. Now, normally that would mean that all the items that you have phrased positively get the same sign here, either all minuses or all pluses. So what you double check as a first thing is, for these, you should check, is it 1, 4, 5, 8, 11, 12, and 17 that are all phrased either positively or negatively. If not, then Stata did something, well, not necessarily something wrong, but something is wrong with your scale, in the sense that there is an item in there for which Stata thinks that it belongs to the set of positive ones, whereas you think, based on the substance of the question, that it doesn't. Quite often, 90% of the cases, you won't see any trouble here, but every once in a while it might happen. So that's the first thing that you have to check. And then you look at these different numbers over there, and the whole aim of this exercise is, well, in this case, 0.82 is already quite decent, but I want to figure out which of these items in there fit the least, and if there are items in there that I should actually better get rid of. let's see. Item test correlation would be, well, I look at the feeling one variable that I have in my data. I look at the happiness variable that I have actually created in my data, and I calculate the correlation between the two. What you want is that this number is relatively high. You want that the whole thing that you're measuring indeed is correlated to each and every one of the separate items. What you do see here is that the correlation is not equally high for each and every one of these separate items. Lower values are worse. And these are, let's say, the first candidates to look at, to get rid of in that particular scale. This one is actually almost the same, because here you could argue that it's a bit of a weird number perhaps, because in the scale score that I create, feeling 1 is in there. So there is a bit of correlation between the scale score that I get and that feeling 1 variable, simply because, yeah, the same thing is in there twice. So what I could do instead is, okay, I take feeling 1, put that aside, and now I calculate my scale score on the numbers 2, 3, 17. And now I check again. Typically what you will get here is numbers that are smaller than the ones that you have over there. But usually the order is more or less the same. And again, you want high numbers here. You want that a separate item is indeed related to the scale score you can create on the other items that you have. Let's see what we have. Where do we start to get bad? For instance, there's this one. So this suggests there is hardly any correlation between feeling 4 separately and a scale score that I could create on all the items except 4. Okay, so this is one reason to get rid of it. Okay, then the one over here is called as the correlation between the items when the separate item is excluded. I think for most practical purposes this can be disregarded, because I've never ever seen that this column would give me something new that I couldn't see on any of the other ones. So in this case I'll simply disregard this. And the easiest one to look at is the last one, because that last one will tell you what will happen with that value over there if you leave out a given item. So this C 0.8311 over there says, okay, if you do the whole analysis again, but now you leave out feeling 4, you get an alpha value of 0.83, which is bigger than the 0.82, not a lot, but a little bit bigger than the 0.82 that you had before. So this is suggestive of, well, if you have a reasonable idea why feeling 4 also doesn't fit very well, if you look at the question, it's sort of weird, I can understand why it might not fit in this big set, then you get rid of it and you try again. And in principle, that thing you can try iteratively. You do it again, you get one of these tables again, and you can check which of the items fits the worst. So let's see, we have here number 4, that is a candidate to get rid of, and which are the 1, 2. I think 17 is the only one, besides 4, that gives a higher number. This is larger, again, not a lot, and that one too. So let's just see what happens if we leave out, did I have that 4 and 17? Yeah, if we leave out 4 and 17, and then we try again. So this one already, no, here you still have them, that one out. Now we try again. Okay, now 0.85. Exactly the same procedure. Now I get a number that's slightly larger. Yes? Depends a little bit. In a minute I'll talk about how to create these item batteries. If this is a known item battery, so there exists a scale, somebody else has tested and retested that whole thing. There are 17 items in there, and with these 17 items you get 0.82, I would leave it alone. And if there is no proof that, okay, if I leave this one out, now I get 0.93, then for that 200 extra, I would just leave it. If it's an existing scale. If it's not an existing scale and it's something that you have come up with, or one person has done it twice and that's it, then I would be a bit more careful and simply say, okay, let's try to make this as small as we can get away with in a survey, and perhaps do the exercise here. And then of course mention, okay, I had 17 items, I looked at which one fit the least, and at least 3 or 4 I show a couple of examples very fast. Then a couple of things that the leftovers or the small print, things you can easily miss if you only get the general hang of it. So what I showed you thus far was from 2 years ago. So now let's do it from start to finish for the same item battery, but now from last year. So first thing to do, you go through the questions and you remember which of these are phrased the other way around. And I made not only a mental but also an actual note. Numbers 1, 4, 5, 8, 11, and 12. These are the ones phrased negatively, and the other ones are phrased positively. I do the same thing. I run my alpha command. I click here. That doesn't seem to help. I now get this, 0.82, already not so bad. So this is, in a way, just fine as is, but let's see how far we can go. We double check with 1, 4, 5, 8, 11, and 12, the ones that have the same sign. 1, 4, 5, 8, 11, and 12, so that's good. No worries there. We check what is the worst here, and the worst is apparently 4. How do we see this? Well, first of all, we can look at the column here. The one that gives the highest increase is our most likely candidate, 0.8239. That's the highest number that we find in this column. That's number 4. And indeed, number 4 also has the lowest number over here, also suggestive that this is a candidate to get rid of. And if we do this, then we see, okay, let's see, we start from 0.82. Now we indeed get that 0.8239. You know, normally I would say good enough, don't mess with an existing scale, but what you could do in principle is continue this iterative process and then keep getting rid of the ones who have the worst score, so to speak. I think I did this a couple times, and I'll show you the end result. So one that I would leave out now would be, let's see, either 11 or 12. There you also see numbers over there that are higher than over there. If you keep doing this, then in the end you end up with this. You have only 1, 2, 3, 4, 8 items left. Now have a scale value of 0.8428. At this point, all these numbers over there are smaller than 0.8428, and none of these are particularly bad. So at this point, certainly there is no reason to do anything else than just stop and say that this is okay. And the only reason why I would ever do this is if I want to rerun the survey and know that I need all the room that I can get, then I would stick to these 8 instead of the original list of 17, in the hope that I can, whatever else it is that I want to measure, that I can fit that in instead of these 10 items. Yes?
What happened to the feeling 6?
Sorry?
I don't see the feeling 6 up there.
Up where? Oh, it's there.
It's here, but on the up, it's not there.
The dash over there, this is saying, okay, take feeling 5 and feeling 7, and all the variables that are in between in the order in which they are in the data set. So not necessarily alphabetical. So if feeling 6 wasn't right between 5 and 7, it wouldn't be included, but now it is, so now it will. Okay, so the only reason to do this if you want to be really efficient in your survey, and then you're good to go. One other example where it works rather well, we asked you what is your general level of trust in foreigners. So a general person of, and then you got a list of 30 countries, and you could rate from 1 to 9 the extent to which you trust somebody else. And the idea would be if we average out that number, that gives sort of an estimate of the extent to which you trust somebody else from another country. This is the alpha command. And here we get a very decent 0.93 here. All the numbers over there are smaller than that 0.93. All these numbers over here are very decent, better than the ones that we had in the previous item battery. So here we could immediately stop. This is quite a decent scale here. It looks like this measures exactly what we want, or at least that all items here correlate very much. So whatever it is that we're measuring here, we measure it in all 13 items. Okay, so that's the standard way to go. So in general, you check the underlying scale of the items. And there is one thing that I didn't focus on just yet. Strictly speaking, all this is based on correlations. And correlations was was actually only meant to be used for interval by interval. We don't have that here. These items are, 5-point, 7-point scales. That's basically it. So officially, we're not even allowed to do this, given that the whole alpha command is based on correlations. But we nevertheless do this sort of by definition. As long as we have at least 5 items in an item battery for each item, we typically find, well, that's good enough. Then, of course, check if the items make sense. Don't just throw everything in one big alpha command. Here, obviously, all these items were meant at the beginning to measure happiness, and for the other ones to measure trust in different countries. I've seen people run an alpha command just on the whole data. That doesn't make sense at all. You first check which of these items are supposed to correlate, and then you do something. You run your alpha, you check whether the right items are reverse coded, you improve when necessary, and then in the end you conclude, okay, this is either good enough, and now I create a new variable. In the beginning, the variable was called happy, and we get rid of all the separate items, we don't use those anymore. Or we conclude, well, there's nothing that I can do here, there's not a single scale that is decent enough to create with these items, and then tough luck. You may have measured 17 items, but none of them is of any practical use. That leaves only a couple things to do, because it has a few options, this command, that we need to focus on briefly. These are the two that I didn't discuss just yet. One is called STD for standardize, and the other one is called as is. And I have to peek if I... No. I have an actual example here. I think I have an example of the standardized and the as is separately, but let's just mention what they are. First, this is asking for, okay, before you do that whole operation with the alpha scores and the whole table and so on, before you do that, make sure that you standardize these separate items. Now, if we have an item battery where all these items are on a 5-point scale, then typically this is not necessary, because given that they are on a 5-point scale, they are on the same scale, roughly speaking, already, so there is no need to actually do this. But if we have separate measurements about something where these separate measurements themselves are on totally different scales, I think in a minute we'll get to a slide where we actually have this. If not, then I'll try to remember that I should mention an example. Then this is a good thing to do. And then what you can find is that if you do not standardize, then it seems as if there's nothing there. If you do standardize, then it does work. I'll show you an example in a minute. The as-is command is if you do not want Stata to mess around with what Stata thinks should be done with the different items, so which one of these should be reverse coded and which ones should not, then you tell Stata to leave it alone. And that however you created these items, that is how you want to define the scale. Typically, if there is one item, for instance, or two in there, that Stata reverse codes, even though that was not what you meant to happen, then the only way to go about it is to say, well, leave that alone. And then think for yourself. First, look at which of these items are the ones that should be reverse coded in actual code, if they are run from 1 through 6. Create a variable equal to 7 minus the original item, that will reverse code every one of them. A 1 will be a 6 will be a 1, and everything in between. And then tell Stata not to mess with it, and then see what happens afterwards. This typically happens if you get a scale from somebody else who says, okay, these are the items, and this is how they should work, and then you find that could be, but in my data they don't. And then the only thing to do is, well, please compare what happens if you do it in accordance with what somebody else has suggested versus if you do it based on what you have in your data. You'll see that in the wiki, the main wiki, there's only one, but it is quite an elaborate one. The question is here to figure out whether we can create decent scales with the data that we have ourselves. And we have 7 or 8 of these item batteries. For each and every one, you can try to figure out if there is a decent scale underneath it, and the procedure is in principle the same all the time. Yeah, let's see. One other reason why that whole alpha idea might work is something like this. For instance, here I have these feeling variables again, and I'm using multiple regression, where the target variable here is net income. That was the estimate that you gave, what it is that you think you will earn when you are 35. And let's see if this depends on your scores on these separate feeling items. If you just throw them all in, Stata will give you an actual answer here. And if you look at all the significances of these variables, you see that, well, only this one, but the rest of them is not significant at So you could be tempted to conclude here, okay, this is not working very well because none of these are apparently predicting very well. So that whole idea that somehow these scores are related to the net income that you give is not working. Otherwise, we would have had way more statistical significances here. But that would be totally wrong. This has again to do with the fact, well, all these coefficients and these statistical significances measure the net effect of these separate variables. So what is the net effect of feeling 1? Yeah, could be pretty decent, but not if we have feeling 2 through feeling 17 included. Then the extra bit that you get from feeling 1 is not so much, and not significantly different from 0. So if you do the actual alpha thing beforehand, so okay, we have here alpha again. I think I include 4 and 8 here. You could think about some other ones as well. Doesn't matter so much. In any case, I create now my variable happy, and I use that happy variable instead of the separate feeling items to see what happens now. Now I run my regression. Net income again is my target variable, but now I use happy as a predictor. Totally significant. Here, there is an effect of that happiness variable, and you see it if you average out all these separate things. And you don't see it if you simply include them all separately. So this is in fact quite a decent predictor. However, if you pay very close attention, you would perhaps have seen that if you compare the two, this is the same one with all these separate feeling variables in there. This one has an R squared of 0.20. This one has an R squared of 0.05, which is certainly lower. So if the only thing that you are interested in is, okay, I'm not exactly sure perhaps what I'm measuring here with these 17 different things, but you know, as long as I predict very well, I'm good to go, then take this one. Even though you don't really know why this is so much better than this. If you're interested in the argument, okay, the thing that I'm measuring here is happiness, and the best way to measure that is by averaging out these separate items. I do not know what I'm measuring here, a lot. Also a little bit of that happiness, but perhaps also something else. So if that's the idea that you're interested in testing, then this is typically what you do. And typically where we find ourselves is in this area. Let's say social scientists or scientists in general. Pretty often we want to know what's going on here, and the only way to try to figure out what's going on is by understanding what it is that you're measuring, and not only by just, okay, let's throw it all in and hope for the best. And there we get our example for the standardization. I thought that there would be an example in there somehow. So this is our example. This is the standard state of car data. We have 1, 2, 3, 4, 5, 6 different characteristics of a car, all measured in different kinds of units. I don't even know them. Trunk is, I don't know, in cubic centimeters perhaps. And weight in kilos, I don't even think that that would be correct because it's American data, so it's probably measured in pounds or something. Then length, let's say in meters, and turn also in meters. Displacement, I don't even know what that exactly would be, perhaps also cubic inches or something. And gear ratio, also not clear. What I do know is that they are not on the same scale. So if I would just think, all characteristics of a car, let's throw them in an alpha command and see what happens. Okay, 0.27. Which is worse than poor. So this is suggestive of not really a scale at all. However, if I standardize these things, realizing, okay, all these are on totally different scales, then you get a very good scale, 95. This is a huge difference. And the only reason is exactly that I do that, because I understand that these things are measured on different kinds of scales. Okay, so it helps to know when to try that standardization. Usually, if you have item batteries, let's say with all 5 item scales, then very often you need not bother. It might be a last resort if you get a very poor scale. Then if it is the case that there are items in there where, let's say, everybody scores 4 and 5 all the time, so you have a really small standard deviation, and there are items in there that are much widely varying, then you could give it a try if it helps, but very often it doesn't help at all. Let's see. What else do I want to have here? Yes. Okay. You could wonder what happens behind the scenes. At least at some point I did. Apparently, I forgot I even had this slide. But here we have the same alpha command again with the standardization included here. I call it car size. And just to see what happens actually, that car size variable, if that is predicted in your multiple regression with the variables that were used to make it, then you see that this is actually what is being created behind the scenes. Minus 3.3, and then here you see all the coefficients of these different variables. So you see here that, for instance, weight gets a coefficient of 0.00 nothing, which is not so weird because weight is, I think, a large number in general. And something like gear ratio gets a minus 0.4. If I do not do this, if I do not do the standardization, then by definition you get equal weights for each and every one of these separate items. So this is also why this is totally different from what we saw before, if we just average out all the separate things. Okay, then that's all about, yeah. In principle, you could, let's say, do what you like in the sense that you could try to come up with an alpha score in the bottom right that is as high as you can get it, and if the standardization helps, do it. The only thing that goes against that is that quite a few of these scales are meant to be designed once and then used and reused. And then what you don't want to have is that you use it and you standardize it because it works well for you, and you use it as well, and you get rid of item 2 and 17 and 8 and 12. And you do the same thing and then reverse code one. So typically, as soon as we sort of have one, then we tend to stick to that one and not mess about too much with it. But in principle, as long as there is no defined scale and you find out standardization is a good idea, do it. As soon as we have one, forget it. Then something that is a bit weird and typically related to the same kind of things that we saw before. So for instance, statistical significance, if your sample is large enough, even really, really small differences will become statistically significant, which is a bit nasty because what you'd like to remember is, okay, statistical significance, great, there is a difference, period. But it's a bit more subtle than that. So here, you see something that is related. You get, in general, higher alpha values, well, the first issue is not so strange. When the correlation between the items is higher. That's exactly what you want. If you have items that correlate a lot, then you get a high alpha score. If the correlations are lower, you get a lower alpha score. But also, there's a strange thing here, is the number of items is higher. If you have more items, you're averaging out more noise. That's sort of the intuition that you could get from this. And for instance, if you have a really low correlation between separate items, let's say 0.1, then even if you have a big bunch of them, that in all likelihood will give you quite a decent alpha value, simply because you're averaging out so much. And here, for instance, for decent correlations, where decent is, let's say, 3, then you can see that if you have more than 10 items, then usually all the items above the 10 that you have do not add very much anymore. That is, the alpha value itself doesn't increase much more. There are a couple of examples in the book where they do the calculations for you and show you exactly some examples where you see this happening, but you shouldn't be, let's say, too happy about that you have a really decent alpha score if you have, let's say, an item battery that is loosely connected but consisting of 35 items. Because that in all likelihood will work whatever you measure. So typically in a survey, if you have 10, let's say, halfway decent items, then you should be good to go. One thing I just wanted to mention in the slides, I mentioned already before, we didn't look at any separation of different ideas, so the trust example could work as well. Perhaps trust is different for, let's say, Western European persons versus all others. That there are really two separate dimensions on the line there. That is something that we cannot test very easily with this, or at all actually, with this alpha command, and that we should do in a different way, and we'll do that in the next course. Then something else that that is sort of an implication of what we've seen before, but not easily realized. Of course, here you get that alpha value, let's say 0.8 or so, and then still this is an estimate of what the true alpha value in the population is. And actually what we would want there is a confidence interval around it. And the only way to do it is through a command that we've done before. Consider that as a bootstrap command. If you tell strings to do this, you get that alpha value and a confidence interval around it, so that you get a bit of an idea as to exactly what a decent prediction for a confidence interval around this value would be. Okay, just as a minor remark. Okay, so now the point would be, you start a survey and you want to measure something, doesn't matter what it is. The most important thing to remember there, and especially if you want to make sure that you do not do something for nothing, is search online. In all likelihood, somebody else has done this before. And it would be really stupid for at least two reasons to try and come up with one yourself. First, it is extra work. If somebody else has done it before, why would you do it again? And the second is, if you come up with a new one, then at some point, if you write about it, you have to explain why, if somebody else did it already, you came up with a new one. Is this better? And then all the stuff that has been tested on the earlier ones, it has been retested, it has been validated, it has been this, it has been that, you have to do that all again. So that's typically not a good idea. And in the professional skills part of this course, in the last week of the course, this is actually one of the assignments that you get. Search for a scale on, and then some topic. And you go on either Google Scholar or somewhere else, simply trying to find somebody else who has come up with a scale for whatever it is that you want to measure before. And there are quite a few. So if you have any choice, then use something that somebody else has done already. If that doesn't work, then try to come up with something that was there already, but that you can adapt at least a little bit to stay close to what somebody else has done already. So perhaps there is a scale for, I don't know, for adolescents, and you can try to adapt it for older people as well. And really the last thing that you want to do is try to come up with the whole list for yourself. Also because that, it's hard to convince a reviewer, somebody else who reads your paper or your manuscript, that it's really necessary to do all that. So here one standard example. If you just type happiness scale, then you already see that, I think this is Google Scholar from last year, maybe the other one is on top now. You immediately see that there are papers where in the title literally is a scale to measure happiness or something of that nature. And then you get quite a few examples. So one of the things would typically be in that whole area of research, would it be possible to use a single item? And how much worse is it if you measure by just a single item instead of through 10 or 12? Okay, let's see. Yeah, a couple ones that you are likely to see, as long as you stay, let's say, relatively close to people around our department. Scales that some of which we have actually designed. So computer literacy, how good are you with a computer? It's relatively straightforward how to measure it. You can ask for different kinds of things to the user. Do you know how to? And then you come up with a list of things that is progressively more difficult. And you try to see, okay, where does it stop? The difficult part there is, of course, that you have to come up with stuff that is, let's say, complicated enough that there are only a couple of people in the population who are actually able to do it. And a standard thing we typically do is we put an item in there. This is also a nice way to check if people are paying attention. That means nothing. That's not so easy, by the way, to come up with a word that sounds as if it is computer related, but really is nothing. And just to see if somebody is paying attention. So you put there, are you able to send bulk email to a large set of people? That really is something, and then you can say, I think I'm able to do that. And then you add, are you able to do some server? You come up with a word that means nothing, and if people then still say, yeah, sure, no problem, then at least you know that they are somehow messing up the result. Satisfaction with gameplay, with movie recommendations, is something that we design ourselves as well. The extent to which you are a morning person, a lot of the research on light, they want to know if you are an early riser or not, because let's say what your biological clock is like. The extent to which you feel immersed in virtual reality or feel threatened in virtual reality. Many of these examples are trying to use scales of the kind that we had before. So item batteries, where we ask you, okay, to what extent do you feel immersed? And what we want to do is actually more of this unobtrusive measurement. So while you are playing a computer game, you're sitting on a chair, there are sensors in the chair measuring the extent to which you move. Want to try to figure out if the movement of the chair says something about the extent to which you actually like the game. that might be one way to do it. Immersion in virtual reality, one way to do it would be in the virtual reality surrounding, there is a door opening, and the door opening is a bit too low. Obviously there is no real door, it's a virtual door, and we check if you do this when you walk like that. And if you do, then apparently you are immersed, and if you don't, then, well, you're not immersed enough. Okay, then one other, no, first, that concludes the main scale bit. Any questions about this? Relatively straightforward stuff, I hope. But nevertheless important to be able to do, because it can give you totally better measurements than what you